So we're diving into the world of quantum mechanics,
That's right.
and we've got excerpts from some great physics texts, to help us along the way.
It's going to be quite a journey. We're going to explore some really intriguing questions. For example, why can't we know a particle's position and momentum with perfect accuracy at the same time? And how is it that particles can act like both waves and particles?
Hmm.
We'll even delve into something that Einstein called spooky action at a distance, which is now known as quantum entanglement.
It sounds like we have a lot to cover. It's hard to believe that over a century ago, physicists thought energy flowed continuously, like a smooth ramp. Then in 1900, Max Planck comes along and kind of throws a wrench in the works.
Yeah.
With this revolutionary idea of energy,
Yeah.
quantum. What's fascinating is that he wasn't even setting out to overturn like the established scientific thinking. He was simply trying to explain something called blackbody radiation.
Right.
And the existing theories just weren't cutting it.
Exactly. Planck was grappling with why the observed light emitted from heated objects didn't match the predictions of classical physics. So his solution was a radical one. Energy isn't emitted continuously, but rather in these discrete packets, which he called quanta. It's like discovering that the universe is built with Lego bricks instead of modeling clay.
Oh, wow.
And Planck's constant, denoted by the letter h, defines the size of these energy packets. It's a fundamental constant that governs the scale of these energy jumps.
So if I understand this correctly, a photon, a particle of light, can only have specific quantized amounts of energy.
Exactly. The energy of a photon is directly proportional to its frequency, and that proportionality is determined by Planck's constant.
So a higher frequency photon carries more energy.
Yeah.
Which explains why ultraviolet light from the sun can give you a sunburn while infrared light just feels warm. What I find interesting is that Albert Einstein later used this quantum idea to explain the photoelectric effect, which earned him a Nobel Prize.
Yeah, the photoelectric effect was another puzzle that classical physics couldn't explain. Shining light on certain materials causes electrons to be emitted, but only if the light is above a certain frequency. Einstein showed that this was because the light had to have enough energy per photon to knock those electrons loose. He proposed that light could behave as both a wave and a particle, which was a pretty revolutionary concept at the time.
So light isn't just a wave spreading smoothly through space. It's also a stream of particles, each carrying a quantized amount of energy.
Precisely. And that's just the tip of the iceberg when it comes to quantum weirdness. It turns out that particles like electrons, which we traditionally think of as tiny balls of matter, can also exhibit wave-like behavior.
Really?
Yeah. The de Broglie hypothesis states that a particle's wavelength is inversely proportional to its momentum, and that proportionality is again determined by Planck's constant.
This wave-particle duality really challenges our everyday intuitions.
It does.
So we have these particles that are quantized and sometimes act like waves. Does this lead us to the Heisenberg uncertainty principle?
It does. The Heisenberg uncertainty principle is one of the most profound and mind-bending ideas in quantum mechanics. It states that there's a fundamental limit to how precisely we can know both the position and momentum of a particle at the same time.
Is this simply a limit of our measuring tools, or is it something more fundamental?
It's not about the precision of our instruments. It's a fundamental property of quantum systems. The more we know about a particle's position, the less we can know about its momentum, and vice versa. It's like trying to grasp a shadow. The harder you squeeze, the more it slips through your fingers.
This raises the question, if the universe is inherently uncertain at its most fundamental level, what does that say about our ability to predict the future?
That's a profound question. Perhaps it suggests that the universe is inherently unpredictable, that even with perfect knowledge of the present, the future remains open to possibilities. But that doesn't mean we can't make useful predictions. It just means we need to embrace a probabilistic view of reality.
It seems like we're just scratching the surface of this mysterious quantum world.
Indeed. The behavior of these tiny particles has profound implications. Think about electrons in an atom.
All right.
They can only occupy specific quantized energy levels.
So it's like a musical instrument where the electrons can only play specific notes.
Exactly. When an electron jumps between these levels, it absorbs or emits a photon with a very specific energy corresponding to the difference between the energy levels. This is actually the basis of spectroscopy, which allows us to analyze the composition of stars and planets from the light they emit.
So this quantum weirdness isn't just theoretical. It's the foundation for much of what we understand about the universe.
Absolutely. It's woven into the fabric of reality. And it's not just about light and electrons. One of the most bizarre phenomena in quantum mechanics is entanglement, which Einstein famously called spooky action at a distance.
I'm all ears. Tell me more about this spooky action and what makes it so perplexing.
Quantum entanglement occurs when two particles become linked in such a way that their fates are intertwined no matter how far apart they are. If you measure the state of one particle, you instantly know the state of the other, even if they're light years away.
It sounds like they're communicating faster than the speed of light.
It's not communication in the traditional sense. It's more like they're two parts of a single unified system. Their properties are correlated in a way that defies our classical understanding of space and time.
This concept of entanglement has far-reaching implications. I've heard it's even a key component of quantum computing.
You're absolutely right. Quantum computers harness the strangeness of entanglement and other quantum phenomena to perform calculations in a completely different way than traditional computers.
It sounds like we're on the verge of a technological revolution.
We are. But before we dive into the world of quantum computers, let's take a moment to appreciate the incredible journey we've taken so far. From Planck's revolutionary idea of energy quanta to the mind-boggling concept of entanglement.
It's been quite a ride, but there's so much more to explore.
There is. And we'll continue our deep dive into the quantum realm right after this.
Welcome back to our deep dive into the realm of energy quanta. Before we went off, we were discussing the mind-boggling concept of quantum entanglement and how it's this key component of quantum computing.
Yeah.
I'm very curious to know how quantum computing actually works. Is it really as powerful as everyone says?
It's a fascinating field, and yes, the potential of quantum computing is immense. But it's important to remember that it operates on principles that are vastly different from our everyday experience with classical computers.
So how is it different? What makes a quantum computer so special?
It all comes down to how information is processed. Classical computers use bits, which are like tiny switches that can be either on or off, representing 1 or 0.
Right.
Quantum computers use qubits, which can be in a superposition of states. This means they can be 1, 0, or both simultaneously.
So it's like having a light switch that can be dim, bright, or both dim and D bright at the same time.
That's a great analogy. And this ability to be in multiple states simultaneously is what gives quantum computers their extraordinary power. And then we have entanglement, which allows these qubits to be linked together no matter how far apart they are, so they can work together on calculations.
It sounds like a recipe for chaos.
Yeah.
How can you possibly control something that's in multiple states at once?
It's definitely a challenge. One way to think about it is that we're not controlling the individual states of the qubits, but rather the probabilities of those states. It's like conducting an orchestra where each instrument can play multiple notes at once, but the conductor shapes the overall sound by influencing the probabilities of those notes being played.
Okay, so it's a matter of orchestrating the probabilities rather than dictating the specific states. But what kinds of problems can these quantum computers solve that classical computers can't?
That's the exciting part. Quantum computers have the potential to revolutionize a vast array of fields. For instance, they could help us simulate the behavior of molecules at a fundamental level, leading to the discovery of new drugs and materials.
That sounds incredible. Could you give us a specific example of how that might work?
Sure. Imagine trying to simulate the folding of a protein, which is crucial for understanding its function. A protein can fold in countless ways, and even with today's most powerful supercomputers, it's a daunting task to simulate all the possibilities. But a quantum computer, with its ability to explore multiple pathways simultaneously, could potentially tackle this problem with ease.
So it's like having a computer that can try every possible combination at the same time.
Right.
It's almost like having a time machine that lets you see all the potential outcomes.
That's a vivid way to put it. And it's not just drug discovery. Quantum computers could also revolutionize cryptography by breaking the encryption algorithms that currently secure our online communications.
I can see why there's so much excitement around quantum computing, but it sounds like we're still in the early stages of development.
We are. Building and controlling quantum computers is incredibly challenging. Qubits are extremely fragile and susceptible to environmental noise, which can cause errors in calculations.
I can imagine. Working with those finicky qubits must be like herding cats.
A very apt analogy. But despite the challenges, progress in the field has been rapid. We're seeing the development of quantum computers with increasing numbers of qubits and improved stability.
It's amazing to think that we're harnessing these strange quantum phenomena, which seem so abstract and theoretical, to create groundbreaking technology.
It is. It's a testament to the power of fundamental research. Sometimes the most profound insights come from exploring the most esoteric corners of science.
So where do we go from here? What does the future hold for quantum computing?
It's hard to say for certain, but the possibilities are truly mind-boggling. Imagine a world where quantum computers are as commonplace as smartphones.
That's a fascinating thought. What would such a world look like?
For one thing, our understanding of the universe would likely be vastly different. We could simulate the behavior of matter and energy at scales that are currently unimaginable, leading to breakthroughs in physics, chemistry, and cosmology.
So we could potentially unlock the secrets of the universe, like how gravity works at the quantum level, or what dark matter and dark energy are truly made of.
Exactly. We could also develop new materials with properties we can barely even dream of today.
And what about everyday life? How would quantum computing impact our daily experiences?
Well, we could see a revolution in fields like medicine, finance, and artificial intelligence. Quantum computers could help us personalize treatments based on an individual's genetic makeup, predict market trends with unprecedented accuracy, and create artificial intelligence that surpasses human capabilities in many areas.
It sounds both exhilarating and a little bit terrifying. But one thing's for sure, it's an incredibly exciting time to be alive and witnessing the dawn of the quantum computing era.
It is, and it's a reminder that we're only just beginning to explore the vast potential of quantum mechanics.
So quantum mechanics isn't just about the weird behavior of tiny particles, it's also about harnessing those strange properties to create groundbreaking technology that could reshape our world.
Precisely. And it all goes back to that revolutionary idea that energy comes in discrete packets called quanta.
It's amazing to think that something so small, like a quantum of energy, can have such a profound impact on our understanding of the universe and our place in it. What's fascinating to me is that this entire field of quantum mechanics emerged from physicists trying to explain seemingly mundane phenomena like blackbody radiation.
It's a testament to the power of human curiosity and the interconnectedness of knowledge. Sometimes the most unexpected discoveries arise from asking simple questions.
I'm curious, are there any other areas of quantum research that are particularly exciting to you?
Well, for one thing, physicists are trying to develop a theory of quantum gravity that would finally unite quantum mechanics with general relativity.
That's the holy grail of modern physics, right? Combining the world of the very small with the world of the very large.
Exactly. Another fascinating area is the study of topological quantum field theories, which explore phases of matter that are characterized by their topological properties. This could lead to breakthroughs in material science and even quantum computing.
So it seems like the journey into the quantum realm has only just begun.
It has. And who knows what amazing discoveries await us as we delve deeper into this strange and wonderful world.
Well, I, for one, am eager to follow along on this journey of discovery. We need to take a quick break, but when we return, we'll wrap up our deep dive into energy quanta with some final thoughts and reflections. Welcome back to the Deep Dive. We've been on quite a journey exploring this mind-blowing world of energy quanta, from Planck's revolutionary idea to the potential of quantum computing.
It's remarkable to think how our understanding of the universe has shifted. Since Planck first introduced this concept of quantized energy. It's a testament to the power of scientific inquiry and our curiosity about the world.
It really is. And what's so fascinating is that this journey is far from over. As we've seen, there's still so many mysteries to unravel in the quantum realm.
Right.
So as we wrap up this deep dive, what are some of the key takeaways you'd like to leave our listener with?
Well, I hope you come away with a sense of wonder at the strangeness and beauty of quantum mechanics. It challenges our everyday intuitions, but it's a reminder that the universe is full of surprises. And as we delve deeper into this realm, who knows what other mind-bending concepts we'll encounter?
It's almost like we've stepped through a looking glass into a world where the rules of reality are completely different.
Yeah.
But even though it seems so strange and counterintuitive, quantum mechanics works.
Yeah.
It accurately describes the universe at its most fundamental level. And it's led to incredible technological advancements.
Yeah, it's a testament to the power of human ingenuity that we've been able to harness these quantum phenomena to create technologies like lasers, transistors, and now quantum computers. And as we've discussed, the potential applications of quantum computing are truly vast, ranging from drug discovery and material science to cryptography and artificial intelligence.
It seems like the future of technology is intrinsically linked to our understanding of the quantum world. But what about the bigger picture? How does quantum mechanics shape our understanding of the universe and our place in it?
That's a profound question. If the universe operates on principles of probability and uncertainty at its most fundamental level, as quantum mechanics suggests, what does that say about our ability to predict the future, or even understand the present?
It's humbling thought, isn't it? It suggests that there are limits to what we can know and that the universe is inherently unpredictable. But perhaps that's also what makes it so exciting. There's always more to discover, always more to learn.
Exactly. And that's the beauty of science. It's a never-ending journey of exploration and discovery. And the more we learn, the more we realize how much we don't know. But that's what keeps us pushing the boundaries of knowledge, seeking to unravel the mysteries of the universe.
It's been an incredible deep dive into the world of energy quanta. A huge thanks to our expert for guiding us through this fascinating journey.
It's been my pleasure.
And to our listener, we hope this deep dive has sparked your curiosity and left you with a sense of wonder about the quantum realm. Keep exploring, keep asking questions, and who knows what incredible discoveries you might make. Thanks for listening.